Hello. In this part of the lecture, we will look at the first order RC and RL circuits. I would like to first go over some properties of the circuits, and then we will look at the first order differential equation and the solution for RC and RL circuits. Then we will move on to talk about problem solving procedures and go through a few examples. So first order RC and RL circuits are circuits that contain either one inductor or one capacitor. So capacitor and inductor are considered as energy storage elements. So in the context of first order circuits, we'll only see one energy storage element. So it's either an inductor or a capacitor that you will see in the examples later. The first order circuit has an exponential response for part of the response. The circuit also follows a differential equation model of the form dx of t over dt, and this is equal to lambda x of t plus f of t. Notice that I have this d over dt. This indicates that I have my first order derivative or the first order circuit. And I also have this zeroth order term, x of t. The lambda over here tells you that I have a natural frequency, and which determines the natural mode of the oscillation. And this lambda can also be expressed in terms of the time constant of the circuit, and this is equal to minus 1 over tau. The f of t over here is the so-called forcing function. So this is like your input excitation, such as voltage source or a current source in the circuit. Depending on the lambda that you calculated, so this lambda can either be positive or negative. For example, if lambda is less than 0 or negative, then I have a decaying exponential response. And as time goes by, you can imagine, since I have this decaying exponential, the system will eventually become stable. Now, on the opposite end, if I have lambda that is larger than 0 or positive, then I have a growing exponential function. So as the time goes by, the system is going to keep going up. It's going to blow up. So the response is going to become unbounded, leading to instability. The solution to the first order equation consists of the natural response and also a forced response. In the natural response, we have this exponential function as indicated earlier, and this is e to the lambda times t minus t0 times x of t0, where this x of t0 indicates that I have some initial condition. In the forced response, notice that the solution contains the forcing function f of t, which is your input excitation in the circuit. The total response can be expressed in several different ways. For example, natural response plus the forced response, as I mentioned over here. Or from the context of differential equation, we can use homogeneous solution, aka complementary solution, plus particular solution. In circuit analysis, we prefer to use something called transient response and steady state response. So when we combine the transient response and steady state response, we can get our total response. So as a reminder, the natural response is a general solution of a differential equation representing the first order circuit. And the natural response is obtained when the input excitation is set to 0. In other words, there is no input. There is no voltage source, there is no current source. However, the response depends on the initial condition. So there has to be initial condition in order for you to have this natural response. And if we go back to look at this part of the equation, it's clear that in order for you to have this natural response, you need to have this x of t 0. The forced response is a particular solution of a differential equation representing the circuit. So in such case, we need to have an input excitation. It can either be a voltage source or it can be a current source. Okay, so transient response is a temporary behavior, and this is the response at time before reaching the steady state, meaning before the circuit settles. So as an example, last time we talked about charging of a capacitor or a battery. So I'm going to use this as an example. So suppose I'm trying to charge a battery and I look at the voltage drop across the capacitor. And this is plotted versus time. And the general behavior, as you will see, looks something like this. And let's just say the final value that I'm trying to charge this capacitor to is 5 volts. Okay. So if I were to mark a point, okay, so let's say somewhere here. Okay, and I'm going to say that this is my cross point, or this is the boundary between the transient and the steady state. Okay. So what this tells you is that if you're to the right of this boundary, okay, so over here, then the circuit or the capacitor voltage is fully charged to 5 volts. But before then, over here, the capacitor is still being charged, right? So it's still in the process of being charged, right? So the behavior of such is temporary. So this part here marks my transient response of the circuit. And while this part here is my steady state. Okay. But then the question is, how do we determine this crossover point or this boundary? Well, so ideally, we wanted to wait for this circuit to fully settle. So that means we want this T to go all the way to infinity, right? So if we're willing to wait for long enough, then we're guaranteed that this capacitor voltage is going to be fully charged to 5 volts, and the circuit is going to be perfectly settled, right? But unfortunately, we don't have this infinity to span. So what we will need to do here is we need to come up with a measure, right? So we need to go by the time constant in this case. So the time constant tau for a simple RC circuit is equal to R times C. Okay, so you just take the product of the RC, R and C to find this tau. And for an RL circuit, the tau is equal to L over R. Okay, so for RC circuits, as you will see, this is R times C, and then for RL circuit, this is L over R, right, or time constant, depending on the context. Now, so in order for you to determine this boundary here, right, so what you will see is that, and I do have a proof on the very last page to show you that if T, okay, is equal to 5 times tau, okay, if T is equal to 5 tau, then you will see that this capacitor voltage is very, very close to the final value. Okay, how close? Well, roughly 99.3% of the final value. So if you take that 99.3% multiplied by 5 volts, then you're basically very, very close to the final value, which is 5 volts in this case. So we're talking about this part of the curve, right? So when the circuit is in a steady state, then we know that we have reached the final value, okay, or very, very, very close to the final value. Okay. So again, we go by the time constant, right? So we don't have this T equals to infinity, so we have to come up with some measure, okay, reasonable measure for us to determine where this boundary is, okay? So we'll use 5 tau in this case. Okay, so next, I wanted to use this simple circuit here to first of all derive a first order differential equation to describe the circuit, and then we are going to come up with the solution for this first order circuit. Okay, so this is what we're going to do next. Okay, so I'm going to start with something that we have already seen. So I'm going to start with KCL. Let me just trying to write something down. Okay, something that we know from this circuit, right? Some facts here. So using KCL. Okay, so I have this voltage source with a resistor and a capacitor, right? So then I have this forcing function, if you will, right? So this is my input excitation um, based on a simple voltage source. And it's an independent voltage source. And I'm going to use a KCL, right, at node A and node B, okay, just to try to write something down that we know of. So first of all, using KCL at node A, I know that the current IS going into this node has to be equal to the current leaving the node, which is IR. Okay, so I have IS is equal to IR. Okay, and then I do the same thing over here at node B. So at node B, I have current going into this node, which is IR, and the current coming out, which is IC. Okay, so IR and IC are the same. Okay, so this simple exercise tells us that the current IR, IC, and IS are all equal. Okay, and where again IS is the current flowing out of this voltage source, and then it's going to go around the loop, right? So it's not surprised that these three currents are the same. Okay, so far so good, right? So this is one outcome that we got from this KCL analysis. And then the next one is KVL, right? So I'm going to start from here. Right? So minus Vs, okay, plus VR, voltage drop across this resistor, plus Vc, which is the voltage drop across this capacitor, and this is equal to 0. Okay, and notice that VR, right? So the voltage VR here is simply equal to IR times R, right? Simple Ohm's law, right? But instead of saying R times IR, I'm going to use R times IC. Okay, R times IC. Okay, because I know IR and IC are the same, so I can use IC instead of IR. Okay, so I have this term here. Okay, now so if we take a look at this equation here, right? So keep in mind our goal here is to come up with first order differential equation that we can use to describe this simple RC circuit driven by this DC voltage source. Okay, so that's our goal here, right? So it does make sense for us to involve some IC here, right? Because we know from last time, IC is equal to C dVc over dt. Okay, so immediately you can see that by using this equation, we can already see the form of this first order derivative. Okay, dVc over dt. Okay, and of course, Vc in this circuit is our variable of interest, right? Because we wanted to know what is the voltage drop across this capacitor. Okay, and then from here we'll be able to make a plot, which is what I showed you earlier, right? You have this charging of this capacitor all the way to some voltage, and that voltage, just to give you a hint here, right? So that voltage is supposed to settle all the way to whatever this voltage is, right? So if I use 5 volts in the example earlier, then it will settle to this voltage, which is assumed to be 5 volts. Okay, so let's carry on here. So this is my equation that I'm going to use, okay, going forward. And so we know VR is equal to R times IR and is equal to R times IC, and IC is C dVc over dt. Okay, so I'll discuss over here. Okay, so now I'm just going to take this and then I'm going to map it over here, right? So minus Vs, right? So still the same copy and paste. Okay. R, okay, times IC, okay, and IC is C dVc over dt, right? Just like I show you over here, plus Vc. Okay, so copy and paste, right? So the only thing that changes over here. Okay, and this is equal to 0. Okay, and the reason it's equal to 0 is because we just did this KVL, right? So remember the algebraic sum, right? So set to 0. So this is our simple first order differential equation that we can use to describe the the behavior of this simple RC circuit driven by this voltage source. Okay, so far so good, right? So we have this equation, then of course we know we need to try to find the solution to this first order equation. So that will come up next. Okay. All right, so from here, right? So from here, what I'm going to do is I'm going to move some terms around a little bit. So I'm just going to take this guy. Okay, so take this term, move it to the other side. So on the left of this equal sign, I have VC minus VS. Okay, so VC minus VS. Okay. On the right side of the equal sign, I have minus RC times dVC over dt. Okay. Move it to the other side, I have a negative sign here. So now I'm going to take integral on both sides. Okay, so integral here and integral there, right? So integral on the left. Okay. And then one more step that I did, or maybe two more, is that I move this minus RC, okay, to here, okay, and then I move VC minus VS to the other side, okay, and then I take the integral. Okay. All right, so now on the left side, I have this minus 1 over RC, okay, integral of this 1 over RC with a negative sign with respect to dt. On the right side, I have 1 over VC minus VS, dVC, okay, with respect to VC. Okay. And then my integrand obviously has to be a function of voltage as well. So V of t and V of t0. Okay, so that's my integrand. Okay, and then now I have this constant, I can take it out. Okay, so take out the constant term, and then I simply just do an integral, okay, of dt, right? So I get t here, evaluate between t0 and t, okay? On the right side here, right? So this is 1 over VC minus VS, right? So you can look it up. You can see that the integral of this is equal to some natural log ln VC minus VS. And then you evaluate between these two integrand. Okay, so B at t0 and B of t. Okay, all right. So then over here, right? So it's plug in t equal to t and minus t equal to t equal to t0. Okay, on the left, and then on the right side, you do the same thing here, right? So you have this VC of t minus VS minus natural log VC at t0, right? So this is the integrand over here. And we know that when we are taking the difference between two natural log, right? So we can have natural log of this term, okay, divided by this term over here. Okay, so instead of taking the difference, right? So now we are doing a division here, okay? So we have this natural log like this, okay? Right. So then since, so we don't like to work with natural log, right? So we wanted to try to get rid of this natural log. So what we do is we take exponential function on both sides, right? So we take exponential on the left and also on the right. So the exponential function on the right side, right, will get rid of this natural log. Okay, so I ended up with VC of t minus Vs divided by VC at t0 minus Vs. Okay, so it's basically just this term here in the bracket. And then on the left side, I have this exponential function. So exponential function raise it up to this t minus t0, okay, negative sign here, divided by RC. Okay, and you may recall this RC is nothing but your time constant, right? So going back to the circuit, I have one R and one C, right? So the time constant of this circuit is simply R times C. Okay, RC time constant. Okay. Okay, so what I can also do here, right? I can further simplify this equation. I can say I can solve for VC of t, right? Because VC of t is really our variable of interest. Okay, so this is our variable of interest. Okay, this is the voltage drop across a capacitor. Okay, so VC of t, right? And notice that this is a function of time. Okay, and if this is a function of time, and then we can come up with this solution, then that means we can make this plot later, right? And I gave you the preview of how it looks like, right? So we will see something like this. Okay, so we will look at this again later. Okay, so move things around, right? So I can solve for VC of t, right? So VC of t turns out to be Vs, okay? And remember, Vs is my voltage source, okay? So for example, 5 volts, right? So this voltage source here, Vs, plus Vc at t0, okay? Initial condition, right? So every time when you see this 0, right? So that indicates that you have some initial condition, okay? So that means, you may have some initial voltage, okay, sitting across this capacitor at t0, whatever that t0 is, right? There's some initial is time instant, okay? So Vc at t0 minus Vs again, right? So it's the same Vs over here, okay, in bracket, okay, multiplied by e raised to minus t0, okay, again, initial time, and then divided by the tau, okay, where tau is equal to RC. Okay, so this is the solution to this first order differential equation for this simple RC circuit. Okay, okay, so let's quickly recap here. So let's just say if T0, okay, is equal to 0 plus, okay, or T0 is equal to 0, right? Let's forget about the plus sign here for a second, right? So let's say my initial time instant is sitting at 0, okay? So what I can do here is I can replace this T0, okay, by 0, okay, or 0 plus, right? So in this case, I haven't talked about why there is a plus sign here, right? But we'll just say, okay, for now, this is equal to 0. So Vc of t is equal to Vs, okay, Vs plus Vc at 0 plus, or Vc at 0, okay, minus Vs times this exponential function, right? So when t0 is equal to 0, so t minus 0 is just equal to t. Okay, so I only have t over here, so minus t over tau. Okay, so now if you look, take a closer look at this equation, right? So remember earlier, we said that the total response is equal to the transient response plus the steady state response. Okay, so now if you look at this equation, right, it's not difficult to see that this part here, Vs, takes care of the steady state, right? Because remember, in the steady state, Vc of t should already reach, okay, very, very close to its final value. Okay, very close to its final value, right? So that means Vs in this case, right? So in other words, from this simple RC circuit, right, the capacitor is eventually going to be charged up all the way to this Vs, whatever this Vs voltage is, right? And I like to use 5 volts as an example, right? So this this capacitor voltage is going to be charged all the way to 5 volts eventually, if you waited for long enough, right? But we know that we don't have this infinite amount of time to wait for this to happen. So we go by this time constant. So if we're willing to wait for, let's say, 5 tau, right, roughly, then we are very, very close to the final value. Okay, so therefore, this term here, Vs, right, is the steady state value. Okay, now anything that is not steady state, okay, for example, over here is considered as transient. And it makes sense because now if you look at this term, right, so I have this exponential function. So this exponential function, okay, comes from the natural response, right? So this exponential function, okay, is going to give you the rest of the response, and this is the transient. Okay, so the transient part is set by this this part of the equation. Okay, so again, the total response consists of 2 parts. One is the transient response, and the other one is the steady state. Okay. All right, so I do have the plots over here. So now if we go ahead and make this plot VC of t versus time, right? So you can plug in a few points and then eventually you will come up with this curve. Okay. So during the transient response, the capacitor is still in the process of being charged up. Okay, let's say you started from 0 volts. Okay, so the capacitor is fully depleted. Okay, it's fully depleted. There's no voltage initially sitting across this capacitor. So in order for you to charge up the capacitor voltage, right, you need to start from 0. Okay, and then all the way to the final value. Okay, so if I were to mark this time instant here, right? So I'm going to say this time instant here is equal to phi tau, phi tau. Okay. So before phi tau, the circuit is still trying to, is still in the process, right, of figuring out, okay, where is the final value and so forth, right? And of course, the process is gradual, right? So you start from 0 volts and then all the way to the final value. Okay, so once you cross this phi tau, okay, then you see that the capacitor voltage eventually is pinned at 5 volts. Right, so let's say assuming this is 5 volts. Okay, so assuming Vs is equal to 5. Okay, so the process is gradual, right? And it goes by this time constant. Okay, and of course you will see that in order to speed up the charging process, right, we want to minimize the tau, right? So that means we need to minimize the product of the R and the C. Okay, RC time constant. Okay, all right. So there is one important concept I wanted to introduce here, and this is something that you will see and also used in the example later. Okay, so the idea here is that at steady state, okay, at steady state, right? So when the cap, right, when the capacitor has been sitting there for a long time, okay, at a steady state, okay, the capacitor, okay, is going to behave like an open circuit. Okay, so this is a kind of an interesting concept here, right? So I claim that the capacitor, okay, has been sitting there for a long time, okay, then that capacitor, okay, is going to behave like an open circuit. Okay, and this is obviously true at steady state, right? Because in a steady state, the t, okay, the time constant or the t is several time constants. Let's say phi tau, right? And so that means we assume that the circuit or the capacitor has been sitting there for quite some time. Okay, and the claim is that if the capacitor has been sitting there for quite some time, then it's going to behave more or less like a very high impedance, okay, high resistance, okay, like an open. Okay, so let's see how we figure this one out. Okay, so let's say I allowed, okay, this t, okay, go all the way to infinity. Okay, so forget about this phi tau, right? So let's say I allow this t go all the way to infinity. Okay, I have infinite amount of time to let this cap sit there forever. Okay, so in such case, we know that since the capacitor, okay, has been sitting there for a long time, right, forever, right? So that capacitor, okay, voltage is already charged all the way to its final value, right? It has to be, right, because it has been sitting there like forever. So the voltage across that capacitor is charged all the way to the final value, right? So I use 5 volts over here. So if it's already charged all the way to 5 volt, so that means there is no more room, okay, for this voltage to change, right? Because the voltage has already been charged, it's saturated, right? You cannot go up nor down anymore, right? It's sitting there, right, for forever, and it has been fully charged already. Okay, so that means that dVc over dt, right? If there is no change in the capacitor voltage, then that means dVc over dt has to be equal to 0. right? With respect to time, right? We're talking about with respect to time here, right? So dVc over dt is equal to 0. No more change in this voltage with respect to time. Okay, so if dVc over dt is equal to 0, this term here is equal to 0, IC is equal to 0, right? One is the cause and the other one is the effect, right? So no more change in the capacitor voltage giving rise to no current. So if there's no current, we know that the capacitor is basically acting like an open, right? Because no current can go into an open circuit. Okay, so that's one way to understand it. The other way to understand it is, well, so I can go ahead and calculate, or I can go ahead and look at the charge, right, from the charge perspective. So if a capacitor is already fully charged, then that means there can be no more change in the charge with respect to time. So that means dq over dt. Okay, so dq over dt is equal to 0. Okay, so if dq over dt is equal to 0, right, and we know that I, the current, is equal to the change in charge with respect to time, then that means the current has to be equal to 0 as well. Okay, so the capacitor is fully charged, dq over dt is equal to 0, so that means the current is equal to 0, and if the current is equal to 0, no current can go into an open circuit, right? So I have an open, okay, for this capacitor, okay, or this capacitor behaves like an open. Okay, so this is one concept that we will see and use quite a lot later when we look at some examples. All right, so alternatively, I just wanted to show you how you can also express this VC of t in terms of the natural response and the forced response, right? So earlier we talked about expressing the total response in 3 different ways, right? So we just talked about the transient and the steady state, right? And perhaps, if you want to express it in a slightly different way, right? So it's still the same VC of t, right? But instead of using the steady state and the transient, right? Perhaps, if you wanted to use the forced response and natural response, right? So the way you do it is you just look for the term associated with Vs, right? Because Vs is the final value, right? And this final value, right? Vs, right, is also your forcing function, right? Remember, right? You have this input excitation, you have this voltage, say 5 volts, right? And this is your input excitation. You excite the circuit with this Vs. So you simply just group the term associated with this input excitation, this Vs, right? And then you group this term, and then you can find your force response. And then the remaining term will be your natural response, right? And as you will see, right, in this natural response, this term is always associated with the initial condition here. Okay, the initial condition, right? Because this is the natural response that will give you the natural frequency, right? The natural mode of oscillation, and that natural frequency or natural mode of operation depends on the initial condition of the circuit. Okay, so if you have some voltage residing across the capacitor at some time instance, right? Some t0, right, initial time instance, then that is an indication of this natural response. Okay. Okay, so let's now talk about, okay, so I wanted to show you just for comparison. So again, the same circuit, right? So I have this forcing function with this resistor and this capacitor. So now I'm going to compare with 2 different taus, okay? So 2 different time constants. One is tau1 and the other one is tau2, right? So let's say tau1 is smaller than tau2, right? So and as for comparison purpose, right, you will see that the one with smaller tau, right, actually gives you faster charging time, right? So in other words, the capacitor will be charged to the final value faster than the one with larger tau. Okay, so the smaller one means faster time, right? So or faster charging, okay, shorter time, okay, and larger tau means longer time, therefore slower charging, okay. But of course, eventually, right? So once you waited for 5 tau here and 5 tau there, eventually you will be sitting, or the circuit will settle, and then you will be at the steady state. Okay, so if you're willing to wait for a little longer, then eventually, yes, the capacitor will still be charged to 5 volt, right? It's just like your battery, right? You have the fast charger and the regular charger, right? The fast charger will charge up your battery faster, right? And that will shorten the charging process. Okay. Okay, just a quick summary here, and this is sort of a very important and it's a universal sort of equation that you can use when you see this kind of first order problem or first order circuits. Okay, regardless of RC or RL. Okay, so it will follow the same form. Okay, so if we're dealing with RC circuits, right? So let's say RC circuits, the variable of interest that we look at is VC of t. Okay, so for VC of t, right? So we'll look for Vs, right? This is the input excitation. So Vs plus the initial value minus Vs again, okay, and then multiply by the whole thing, okay, in bracket, multiplied by the exponential function, okay, and over here in the denominator we have this tau, right? Remember, this is my time constant RC. Okay. Another way of expressing or understanding or representing this VC of t is we use something like this where we look at the VC at infinity, right? So inside here we have the t, right? Time. So when t is equal to infinity, we know that this corresponds to the final value. Okay, so VC at infinity plus VC at 0 plus, okay, the initial value, right? So instead of using T0, right, if I were to replace this T0 with 0 plus, okay, or 0, right, then I have my initial value, okay, so VC at 0 plus, okay, minus VC at infinity, okay, so again, this is my final value, okay, and then whole thing multiplied by the exponential function, and since T0 is now equal to 0 or 0 plus, then I can simply just look at a t over here on the top divided by RC. Okay, again, this is my time constant. Okay, then of course, qualitatively, what you can do is you can say this is my final value. All right, so plus the initial value, which is this term here. Okay, so this is this. Okay. Minus the final value again. Okay, multiplied by the exponential function. Okay, minus elapsed time divided by the time constant. Right. So this means t is always increasing, right? T is progressing, and then as t goes up, right, you have this e to the minus t over tau. Okay, and to the minus t over tau, right? So then you will see that you can plug in t equal to 5 tau, right? And then you can do the evaluation in this case. Okay. Okay, so now similarly, if I were to generalize this expression, okay, or this solution here, right, make it universal. So instead of writing just the VC of t, right, I'm just going to use x of t. Okay, so if you're dealing with RL circuits, okay, if you're dealing with your RL circuit, you will still be following the same form. Okay, this is like a template, right? This is like the template which is derived earlier for the first order system. Okay, first order circuit or first order system, right? Okay, so instead of using v, right, I'm just going to make it general, right? So x of t is equal to x at infinity plus x at 0 plus minus x at infinity, and then holding multiplied by the exponential function here. Okay. Now, since this is universal, so depending on you're dealing with RC or RL circuits, right? If you're dealing with RC circuits, then you replace this x by VC of t. If you're dealing with RL circuits, as you will see later, then you will replace x of t by IL of t. Okay, so for RC circuits, we are interested in the capacitor voltage. In the RL circuits, we are interested in the inductor current. Okay, so this is for RC circuits, and then this is for RL circuits, right? They're both first order. Okay, first order, right? So only contains one energy storage element. One is the capacitor, and the other one is the inductor, right? So you always have this resistor here, right? RC and RL. Okay, and then just like what I alluded earlier, so tau for RC circuit is the product of R and C, and then the tau for RL circuit is L over R. Okay, it's taking the ratio. Okay, I wanted to go over this example as a warm up, okay, just to show you how you can utilize this generalized equation that we derived, okay, to understand the behavior of the circuit in this first order system or first order circuit. Okay, so in this example, I have two resistors instead of one. Okay, so if you look at the previous, example, I have one resistor only, right? And then in series with the capacitor. But now I have R1 and R2, okay? And I still have this VS, input excitation, forcing function, okay? Forcing function, okay? Then, of course, the goal is still to find what is the capacitor voltage, right? The voltage drop across this capacitor, okay? Okay, so without having to rederive, the first order equation and therefore the first order solution, because we have already done that already, right, earlier, and then we arrive at this solution. This is our template. So I'm just going to make use of this template, okay? And I'm going to show you how to use this template, right? And we need to solve for VC of t, okay? So to solve for VC of t, or to find this VC of t, we will need to build in this this equation, this template, right? And then some of the uh, the variables that we need, okay? Some of the variables or parameters that you need here are your VC at infinity, okay? VC at 0 plus, and then also the RC time constant, okay? So they're basically three parts, okay? So this, okay, this variable here, or this term here, and then this RC time constant, okay? So once we figure that out, we just have to put everything back to this template, then we are done. Okay, so this is how you use this, make use of this template that we just derived, right? Okay, so first thing first, so let's see. So I have two resistors here, one capacitor here, and then let's see what is given to us. So VC at 0 plus, okay? So this is the initial condition, okay, that we need in order to complete this part of the equation, right? We know the final value, okay? We have the initial value and the final value, but we need to fill this one out, right? So the initial condition here, the initial value, VC at 0 plus, right? This is assumed to this, we can assume that this is already given, okay? So we assume that this VC at 0 plus is equal to 2 volts, okay? And we assume that this is given to us, and otherwise we will have to find it, okay? And in the subsequent examples, we will practice finding this VC at 0 plus, okay? And I'll quickly remind you, right? If you recall, in the last lecture, we talked about property of continuity, right? So that's where this plus and the minus sign comes in again, Okay, so we will figure out, why there's a plus sign, okay, in a second. Okay, but for now, let's assume that this is given to us already, and this is 2 volt. Okay, so that means my initial voltage, okay, across this capacitor is equal to 2 volt when T is equal to 0. Okay, so that's how you interpret this. Okay. How about VC at infinity? Okay, VC at infinity. Well, why do we need VC at infinity? Well, so we are trying to figure out the final value here. Okay, we're trying to figure out the final value here. We're given the initial value, okay, that we don't need to find. Okay, so we can just plug in here, but we still need to figure out the final value and also the tau. Okay, so those are the two tests that we need to find. We need to do. Okay, so to find VC at infinity, okay, so if you look at this VC at infinity, this means that T is equal to infinity. T goes all the way to infinity. Okay, so this tells us that this circuit, okay, this entire circuit, including this capacitor, has been sitting there forever, has been sitting there for a long, long time already. Okay, and recall what we just talked about, right? So if a capacitor has been sitting there for a long, long time, then that means this capacitor behaves like an open circuit, right? So if it's sitting there for a long time already, then that means this capacitor is fully charged. And if it's fully charged, then there can be no more change in the capacitor voltage. Okay, so that means there is no current going through this capacitor, and therefore this capacitor behaves like an open. Okay, so if this capacitor behaves like an open, right? So I'm just going to momentarily cross this one out, right? Since this is now an open, okay? So instead, what I need to find is this VC, okay, when T goes to infinity. So VC at infinity, right? A little redundant, but this is how it came about. Okay, so VC at infinity. Okay, so when VC is at infinity, okay, then this capacitor is open, right? Cross them out, across this one out, and I just need to find the voltage drop across this open. Okay, this open, these 2 dots. Okay, and we know that a voltage division will do it, right? To find the voltage drop across these 2 dots, all I have to do is to find the voltage drop across this resistor R2, right? So I'll do R2 over the sum multiplied by Vs. Okay, so R2 over the sum multiplied by Vs, and that will be my VC at infinity. Okay, so it's the same explanation I gave you earlier, right? So when T goes to infinity, cap has been sitting there for a long time, and dVc over dt is equal to 0, therefore IC is equal to 0. Okay, so no current can pass through an open circuit, and therefore this capacitor behaves like an open when it has been sitting there for a long time. Okay, okay, so we found VC at infinity. Okay, VC at 0 plus is already given to us, right? So we are down to just one more variable or parameter that we need to find, okay, in order to complete this template or this equation, right? So that last parameter that we need to find is the tau, right? The time constant. So tau, we know, is equal to R times C, right? RC time constant, right? But in this case, we have 2 resistors. Okay, we have 2 resistors, R1 and R2, right? In the last example, we only deal with 1 resistor, so that's simple, right? So there's only one, so that has to be the one, the only resistor that we use in the equation, right, for the RC. But now I have R1 and R2, so how do I figure this one out? Okay, so for this resistor, okay, or for this tau, right? And for this tau, we need to find the equivalent resistance. Okay, not just R1 or R2, but we have to find the equivalent resistance. Okay, and this equivalent resistance concept is basically the same as your Thevenin or Norton equivalent circuit, right? So if you recall that in the lecture when we talked about Thevenin and Norton, right? So we had to deactivate, okay, deactivate the sources, okay, all the sources, okay. So for voltage source we short it, and for current source we open it, okay. So in this case we have a voltage source here. So to find this uh, resistor Req, we short this guy out, okay. And of course, now what you do is you imagine, okay, you are this capacitor, right? So now this capacitor is no longer cross out, right? So imagine you are this capacitor, right? You're standing right here. Let's say stand right here. Okay. And do the same thing. You look all around you, right? So you look to the top, look up, look down, and then look to the right. You don't see anything. Okay. But when you look to the left, what do you see? Right? You are this capacitor, right? So you don't see yourself, okay? So you see R2 and R1, right? But this voltage source is shorted out, okay? So this capacitor sees R1 and R2 in parallel. Okay, so R1 and R2 in parallel, so that will be your equivalent resistance, Req. Okay, so that is the resistor that you need to use in order to calculate your uh, tau correctly. Okay, you can't just use R1 nor R2. You have to use the equivalent. Okay, so in this case is R1 in parallel with R2. Okay. Now the last step is quite straightforward if you remember this template, right? So this is already derived, and you should try to make good use of it, right? So remember this template, right? That you need to have this final value, and then inside this bracket you have the initial minus the final, and then multiply by the exponential function, right? So you basically just need to fill out this term one by one. So VC at infinity is nothing but this, okay? VC at 0 plus, right? This is already given to you as part of the question. VC at infinity again, right? This term is the same as this. Inside the bracket, right? So take this minus this, multiply by the exponential function. Okay, and in the exponential function, I have this tau on the bottom. Okay, so this is my tau, and the tau is calculated as Req times C, right? Where Req is R1 in parallel of R2. Okay, so once you figure out this tau, right, you can just plug in here. Okay, and then you're done. Okay, so that's the entire process for you to find VC at V or VC of T. Okay, VC of T. Okay, so now there's one more concept I wanted to introduce here. So later on when we analyze the circuit in examples, you will see that there will be some switch or switches depending on the problem involved in the circuit. Okay. So why do we need a switch? Well, so in general, we are trying to understand what happened to the response of this circuit, okay, due to any abrupt change, okay, any sudden change that we introduce to the circuit, right? So to emulate that kind of scenario, right? So one thing that we can do is we can just use a switch, okay? Whether it's a mechanical switch or electronic switch, but of course, in this course, everything is electronic, right? So we will use the electrical switch to emulate this switching event. Okay, so we'll see that I can turn on and off the switch, right? So that means I can create two different scenarios. One is before the switching event, and the other is after the switching event. Okay, and I can monitor what happened to the behavior of the circuit before and after the switching event. Okay, and typically what we assume is that before the switch is flipped, okay, so before you change the position of the switch, right? So we assume that the circuit has been sitting there for a long time, and the circuit has reached its steady state. Okay, that's before you flip the switch. Okay. Now once the switch is flipped, okay, that means the circuit, okay, is disturbed, okay, because right now you introduce this sudden change, okay, to the circuit. So the parameter in your circuit is going to be different, okay. But this behavior is going to be temporarily, right? Because we talked about the transient behavior, right? So once you disturb the circuit, right, then the transient behavior of the circuit kicks in, okay? And of course, once you waited for around 5 tau, right, then the circuit eventually is going to settle again, right? Because it will be operating in the steady state, okay? So that's kind of the situation we wanted to create using switch or switches, okay? So let me quickly talk about the how we should interpret this switch, okay? So the symbol that you use to represent a switch looks like this, where you have a hinge, okay? And then you have this arm that can move, okay, between open or close, okay? And I have point A and point B, right? So when this arm is closed, then I have electrical connection between point A and B. Otherwise, this switch is open, okay? Then there's no connection, okay? So the way we interpret this arrow here, right, is that so this arrow is pointing downward, okay? So that tells you that the switch, okay, is only closed, okay, at t equals to t0, okay? When the switch, so when t is equal to t0, that's the only time this switch is going to be in the closed position, okay? The closed position over here. Okay, and that's how you establish the electrical connection between point A and B. Okay, all right. So again, when t is equal to t0, this arm, okay, is moved from this point to this point. Okay, so following this arrow here, right? So let's say if I have an arrow that is pointing upward, right? So then the way you should interpret this is, when t is equal to t0, then the switch is open. Okay, because if the arrow is pointing upward, right, then you know that there will be no connection when t is equal to 0. Okay. All right. So why is this used, right? So well, if you think about it, essentially what we're trying to do here is we wanted to create this unit step function mathematically, right? We wanted to say that, okay, when t is less than 0, right? When t is less than 0, I'm on the left side of this y-axis, right? So when t is less than 0, I have no voltage, 0 driving function, or that driving function, that voltage source is equal to 0. So, and when t is greater than 0, okay, all of a sudden, right, the switch is flipped, then I'm now pinned at 5 volts. So I wanted to create this step function, okay, going from 0 to 5 volts. Okay, so this is what we are trying to do here. Okay, so from minus infinity to 0, or 0 minus, right, the time instant right before 0. Okay, so I'm operating over here, okay, with 0 volts for my forcing function. And when t is between 0 plus and infinity, then we have 5 volts, okay, all the way. Okay, so by using a switch, right, we can do the same thing, right? So if you look at this connection, this configuration, I have a switch here, okay. Before t is equal to 0, okay, before t is equal to 0 or 0 plus, my switch is sitting at position A, okay. So this means that this arm here is connected to ground, and we know that ground has 0 volts, right? So that means when you're sitting at position A, this point here, this voltage here is equal to 0. Okay. When t is now equal to 0 plus, okay, now this switch, okay, the position of the switch is going from point A to point B. Okay, so we are here. So now if I'm at point B, right, so let's say over here, right? So now I have this electrical connection between this point and this point. So now this voltage is equal to 5 volt. Okay, so I can basically use this switching concept or switch, okay, to represent my mathematical function, right? In this case, it's a step function, right? Going between 0 and 5 volts instantaneous. Okay, so this is by just a flip with a flip of a switch. Okay,